Good afternoon, everyone. My name is Nicola Doppio from HIT, Hub Innovazione Trentino. Welcome, everyone. You're here taking part to the final event of the PROTO Challenge 2021 edition. This is the third edition. We've been running this innovation contest since 2018. For those of you that do not know what the PROTO Challenge is, it's an innovation contest that allows manufacturing companies to get in touch with university students and young researchers to implement their capacities to make the best use of additive manufacturing and the design competencies related to design for additive manufacturing. The students have been collaborating together with 5 selected companies over the last basically 3 months. So it's a very long process behind the presentation of the results today. And today we are very excited to get to know about these results. Okay, so here in the room with us, in the Zoom room with us, there are connected 5 companies and their representatives, and also 35 solvers from the University of Trento. And first of all, let me thank very much both the 5 companies and the 35 students that have been collaborating together during the PROTO Challenge over the last 3 months. Now it would be time to make an applause. We cannot do any applause, and we also tried to understand whether there was any technical options for having a virtual applause, but apparently it's very hard to do. So thank again very much to the participants. And also, as you can see in this slide that I'm showing, there are many partners of HIT without whom it wouldn't be possible for us to host such kind of events. Of course, the University of Trento, especially the Department of Industrial Engineering, but also Trentino Sviluppo, along with Polo Meccatronica and the PROM facility, Confindustria Trento, the C-Lab from University of Trento, Neutech Park, the Digital Innovation Hub Trentino Alto Adige, Südtirol, and nTopology. Thank you again very much to all the partners for making this possible. Okay, so without further ado, and before entering into the contents of the today event, I would like to give the floor to our President, Paolo Girardi, for the initial greetings. And now I'm going to switch back to Italian. Quindi Paolo, prego a lei per le presentazioni iniziali. Ah, Paolo è ancora muto? No, al momento non la sentiamo.
Mi sentite?
Adesso sì, fantastico.
L'abbiamo fatta. È stata complessa sto giro, far funzionare la tecnologia, uno spettacolo. Comunque grazie Nicola, grazie mille a tutti quanti, un benvenuto a tutti a questo evento che credo che rappresenti un momento assolutamente chiave all'interno delle attività che vengono svolte da HIT. Prima di iniziare però ci tengo anche a portare a ciascuno di voi i saluti dell'assessore Spinelli, che fino a questa mattina era in agenda per poter partecipare a questo evento, perché come già fatto in altre occasioni in passato, appunto ha sempre tenuto molto a esserci, per l'importanza dell'evento e per ciò che l'evento rappresenta per il sistema trentino. Ahimè, questi sono periodi dove in particolar modo il suo assessorato è particolarmente sotto stress con le manovre economiche che ci sono in corso, e quindi appunto obtorto collo ha dovuto rinunciare, ma mi ha chiesto in maniera esplicita appunto di salutare ciascuno di voi, di augurare un in bocca al lupo a tutti, e di rinnovare il suo interesse. Poi la prendo come una promessa appunto nell'esserci alla prossima iniziativa, al prossimo anno. Quindi detto questo, quindi un in bocca al lupo da parte sua a tutti. Ci tenevo appunto a rappresentare quello che è il grande interesse che IT ha per questo tipo di evento, perché è veramente un evento di sistema. Nicola prima ha citato tutti i partner che a diverso titolo hanno partecipato alla creazione, alla progettazione, alla creazione e alla realizzazione di questo evento. E quindi non li ricito, ma li ringrazio tutti. Vedo presente Mirko Cainelli negli alcuni video che riesco a vedere, poi ce ne sono tanti altri che non riesco, quindi Confindustria, ma appunto Trentino Sviluppo, l'università, no? Quindi insomma tutti i vari soggetti. È un evento, un vero evento di sistema, è un evento dove l'alta formazione, la ricerca e le imprese sono a contatto operando in maniera fattiva per la risoluzione di alcune sfide tecnologiche. È quindi l'occasione per contaminarsi, non si dovrebbe usare in questo periodo questa parola, ma rende assolutamente bene le idee, contaminarsi reciprocamente per far conoscere al mondo delle imprese le grandissime, altissime professionalità che ci sono nel mondo universitario, nel mondo della ricerca, per far sperimentare alle giovani leve dell'ingegneria del futuro quello che è la possibilità di applicarsi a problemi concreti che le aziende si trovano tutti i giorni ad affrontare, che riguardano i loro prodotti, che riguardano soluzioni di questioni che per loro possono voler dire sviluppo, innovazione o esistenza alle volte, quindi competitività di mercato di sicuro. Quindi è un evento in cui la presenza di tutti voi, sia le aziende che sono state selezionate per appunto essere oggetto di questa sfida, e piuttosto che tutti i docenti, ricercatori e voi universitari che avete partecipato e contribuito con la vostra competenza e genialità alla risoluzione di questi problemi, è un evento che come si chiama? Vuole essere, come dire, un sasso che poi, gettato nello stagno, si propaga come onde in tutto il sistema economico trentino, perché possano sempre di più vedere nella ricerca, nell'università, un partner, e quindi anche in voi che siete il futuro, dei partner appunto con cui sedersi e fare realmente innovazione, confrontarsi per fare realmente innovazione. Siete passati attraverso, sperimentando quella che è l'applicazione della manifattura additiva, no? Che è come dire, uno degli elementi chiave, no? nel traghettare l'industria italiana verso il paradigma dell'industria 4.0, che attraverso le tecnologie digitali di fatto permette di risolvere cose che prima appunto era impensabile, improponibile poter fare. Quindi è stato, sentendo anche i colleghi, un'avventura assolutamente affascinante, interessante, e ne approfitto anche proprio davanti a voi per ringraziare i colleghi Luca Mion, Nicola Doppio e Vesna Misic per l'impegno che hanno profuso in quello che, come mio desiderio, come desiderio di IT, vuole essere solo un primo passo di un percorso, per quanto oggi siamo qui per l'evento finale di questo momento di challenge, ma vuole essere il primo passo in un percorso di contaminazione e collaborazione che vorrei diventasse sempre più forte, sempre più quotidiana tra il mondo della ricerca e il mondo delle imprese. Desidero pertanto augurare a tutti quanti voi ringraziarvi innanzitutto per quello che avete fatto e augurare un grosso in bocca al lupo per quello che sarà il futuro ciascuno di voi personale, e anche appunto per le imprese, appunto in quelle che saranno, che siano efficaci e interessanti le soluzioni che sono state progettate. Grazie a tutti, in bocca al lupo e buon lavoro.
Grazie mille Presidente per aver spiegato perfettamente anche lo spirito dell'iniziativa Di nuovo anche qui ci starebbe un bel applauso, ma non si può fare. Adesso darei la parola a Mirko Cainelli di Confindustria Trento, anche da parte sua per i saluti iniziali. Prego Mirko.
Buon pomeriggio a tutti, buon pomeriggio Paolo e buon pomeriggio a IT per l'invito a questa videoconferenza. Innanzitutto saluto tutti voi per questo evento perché è l'ennesima edizione vincente della Proto Challenge. Anche quest'anno abbiamo visto prima quanti siamo collegati, si evidenzia una partecipazione molto numerosa sia in termini di aziende che di studenti. Questo sottolinea senz'altro la bontà del progetto e le ripercussioni positive che può generare sul nostro tessuto territoriale, sulle nostre aziende. Da parecchi anni la nostra associazione crede in queste iniziative di Open Innovation per una contaminazione reciproca tra il mondo della ricerca, l'università e le imprese. Per innovare servono idee, prodotti, talenti, ma non tutto può essere effettuato all'interno dell'azienda. Ciò che accade fuori dall'azienda va considerato la stregua di ciò che nasce dentro, basta che sia coerente con il business model dell'azienda stessa. L'accelerazione che stiamo vedendo un po' tutti nella digitalizzazione, determinata in special modo dalla pandemia, ha reso sempre più necessario un utilizzo integrato da parte delle aziende delle tecnologie abilitanti di Industria 4.0, in particolare diciamo sulla prototipazione rapida, col conseguente utilizzo dell'additive nella manifattura. Uno degli insight chiave conseguente alla manifattura globale è che indipendentemente dal settore dell'ubicazione, le aziende guardano all'additive per rafforzare la partnership con i propri OEM, per mettere in atto strategie di sviluppo e creare prodotti sempre più innovativi con lead time bassissimi. Il time to market, spesso viene ribadito dai nostri clienti, sarà sempre più una leva vincente anche nel futuro nelle fasi di ingegnerizzazione e di sviluppo di un nuovo prodotto. Ciò è evidenziato da un investimento crescente nel 3D printing, che lo vediamo costantemente, e viene riconosciuto come una valida alternativa alla prototipazione standard nelle fasi di sviluppo di un nuovo prodotto. Il settore manufacturing a livello globale sta dimostrando l'esigenza di una maggiore resilienza della supply chain, di tutta la parte della fornitura. Richiede una incrementata flessibilità produttiva, una più alta velocità di innovazione e una elevata sostenibilità ambientale. Specialmente il discorso della sostenibilità è sempre più evidenziato in questa fase finale, speriamo, della pandemia, e spesso è sottolineato dalle esigenze trasversali che vediamo a livello mondiale. Le principali aree di innovazione per le aziende stanno prendendo in considerazione la personalizzazione di massa per prodotti diretti al consumatore, la produzione on demand e il magazzino digitale virtuale. In particolare, da analisi che abbiamo fatto, il 91% degli intervistati di un recente rapporto di HP vuole esplorare l'innovazione che la mass customization offre e ritiene potrebbe essere applicabile alla propria attività se le parti, se i prodotti potessero essere personalizzati attraverso il 3D printing, additive e quant'altro. I settori medico, industriale, automobilistico, noi siamo nel settore automobilistico che in questo momento è molto in crisi, ma essendo in crisi è proprio in questi periodi di crisi in cui viene richiesta una maggior velocità di innovazione e di sviluppo relativamente a nuove tecnologie. E stiamo vedendo proprio come i nostri clienti ci chiedono l'utilizzo di queste nuove tecnologie per dare maggiore enfasi al time to market. La principale barriera d'ingresso che vediamo nel settore dell'additive è quella di trovare una forza lavoro qualificata. Per affrontare questo deficit di competenze, il 64% degli intervistati vuole offrire più servizi di formazione professionale e il 53% desidera che le aziende, i governi, le istituzioni e i cittadini lavorino insieme per investire in programmi di formazione e job skilling. Questo per dire semplicemente che quello che state facendo è estremamente interessante e utile per lo sviluppo futuro. Come Confindustria ci crediamo e ben volentieri supportiamo al massimo iniziative di questo tipo. Grazie a voi che le state portando avanti con volontà e determinazione e vi auguriamo un ottimo lavoro.
Grazie mille a Mirko Cainelli, vicepresidente di Confindustria Trento con delega all'innovazione, lo sviluppo e l'impresa 4.0. So now it's time to switch back to English, if you don't mind. And it's time to look into the agenda of the today event, which is very packed. So buckle up because we have a lot of content to go through. I will start along with colleagues of mine, providing you a short introduction about what the Proto Challenge is and how it works. And then I will give the floor to Trevor Laughlin from nTopology for the first talk, Advanced Geometry Representation in Design for Additive Manufacturing. After that, we will go through all the presentations from the teams of students about the results developed during the Proto Challenge to the 5 challenges casted by the 5 selected companies. And then there will be a final keynote speech by Paolo Gennaro from Georg Fischer Machining Solutions. And Paolo will, discuss about when additive manufacturing is really worth and why it's not, okay? Because it's not always worth. And of course, last but not least, there will be the final awarding of the winning team, okay? So stay connected until the end because there will be a lot of content to share with you. Just a quick technical message, please help us spreading the voice about this innovation contest. Please do write some posts on your social media and follow that hashtag that you can see, hashtag Proto Challenge, and feel free to use it, of course, to maximize the dissemination of the event. Also, the Proto Challenge happens in the context of 2 European projects that we are part of, Additive and PROTO. And also there's a strong support from the European Commission about this kind of initiative. What else? Of course, we have people connected from abroad, project partners connected from abroad. The event is streamed online on the Facebook page of Hub Innovazione Trentino. So feel free to let the people know. They can connect and follow the event on our Facebook page. And just 2 practical things for you. Make sure that all the participants connected in the Zoom meeting are muted. And also from now on, please do switch off the camera if you're not the speaker in a way that all the presentations will be very much focused and there will not be distraction. And at a certain point, we will ask you to switch back your screen on because we will take a family picture all together. But for now, for the time being, we will keep the video switched off. All right, so I will now like to spend a couple of minutes involving my colleagues Silvio Antonioni and Vesna Misic, who were totally involved in preparation and management of the Proto Challenge, to let you know how the Proto Challenge is possible and how it works. So the first thing that we did back in November and December last year was to select the companies. So there was a selection process for the company. So Silvio, would you like to tell all the participants something about that process?
Hi, Nicola. Hi to everyone. Thank you for giving me the floor. It's been a great journey till now. And I have to admit that we had a lot of companies that submit their proposal for participate actively in the Proto Challenge. And among all these companies, we have selected 5 of them, thanks also to the student that they giving their to the Proto Challenge. And we have selected with a commission 5 companies that are Lincotech, that they are producing medical devices with additive manufacturing technology. PAMA, that they are manufacturing boring milling machines and machine centers with a very big dimension capacity. Leoni and Vianello, that they are a design studio with a professional postural trainer. La Sportiva, that they are the leader in the mountain clothing and shoes. And Solid Power, that they are producing commercialized solid-state batteries. I have to admit that I've seen a very good project along running the period. I've been monitoring the status of the development. And I have to mention that all the results from coming from the student, coming from the team, and all the IPR, the intellectual property right generated, is owned by the company. I think that this is a very added value for the companies. They know that they can continue improving, selling, commercialize, or starting from that point and to bring to the market this solution without having any problem in the future. This is the status of where we achieved now. So I give the floor to Vesna so she can speak about the solver and the process, how they have been engaged. Thank you, Nicola.
Thank you so much, Silvio. Indeed, on the other side, we had to select the solvers that went through the activity of designing solutions to the challenges provided by the company. So Vesna, how was it possible? How hard was it to manage the whole process of selection of the students?
Thank you, Nicola. Well, for this edition, we have selected 35 students coming from 2 different departments. So from the Department of Industrial Engineering and from the Department of Civil, Environmental and Mechanical Engineering from the University of Trento. We have selected them, and then based on their background, we have matched the teams with the companies and with the challenges. As regarding the remote setting, the team, each team interacted remotely with the company on a weekly basis and sometimes twice a week too, in order to have feedbacks and in order to discuss ongoing results with the company. But the most important part is that this collaboration between the team and the company in a remote setting was made possible because they organized their work with the use of a sharing platform, which is a mirror board, that is meant for team collaboration. And also this platform helped us to monitor the process of their work, which was amazing. So this is how we selected, and this is how they worked, and the remote setting was perfectly functioning for this edition. So
thank you.
That's all.
Thank you so much, Vesna. Yes, the whole process was, of course, carried out in full online and remote setting. And by the way, I have to thank very much Professor Paolo Bosetti and Professor Matteo Benedetti, who are connected today, because they helped, of course, a lot in getting in touch with students and selecting the students to the challenge. But hey, the teams wouldn't have been able to get the final results without the help that they had received by 5 mentors who are young engineering and additive manufacturing and design professionals, which you can see in this slide. Matteo Perini from Prom Facility, Ciro Malacarne and Gianluca Berti from Prom Facility, and Raffaele De Biasi and Simone Murchio from the Department of Industrial Engineering of the University of Trento. The mentors were in touch on a weekly basis with the teams, and they were helping a lot the teams in getting to the final result. So thank you so much to all mentors, because again, teams wouldn't have made it without you, okay? And of course, teams will be evaluated. So that's why we are here. Today, we're going to present the results and also award the winning team. So those that you can see in these slides, in this slide are the criteria that were used by an evaluation commission to evaluate the results. Okay, so we have ability to perform the activities correctly, the completeness of the results, the innovativeness of the results, the potential business impact of the results provided, and also the effectiveness of the presentation. Okay, so the presentation that will be given today by the teams will also be evaluated, and the evaluation commission is formed by Professor Paolo Bosetti, Professor Matteo Benedetti, and our colleague Silvio Antonioni from HIT. Okay, and that you can see on the right side of this slide is a tablet, which is the prize for all the participants of the winning team. There will only be one winning team. And of course, the challenge wouldn't have been possible without a technical partner who has provided the software, advanced design and simulation software for additive manufacturing, that this year was nTopology. Okay, nTopology was so kind to make available free licenses of use of the software to the students and the mentors, and also provided very valuable initial training to the students before the beginning of the challenge. Again, this wouldn't have been possible without nTopology. So now I would like to give the floor to Trevor Laughlin, Vice President of Product from nTopology, for a presentation from their side. Trevor, the floor is yours. You can now start pulling up your slides.
All right, thank you, Nicola. Let's see here. Share my screen. Okay, if everyone can see my screen, I think we're ready to start.
Yes.
So,
yep.
First of all, thank you for having me. Really excited to be here. Really looking forward to seeing all the results in a few minutes. So I think what we're doing in nTopology fits really well with the spirit of this event. So I think we're going to see some really good stuff. So I have a few minutes here to talk a little bit about one aspect of nTopology, specifically around the geometry representation, and touch on that a little bit. And so we'll go through that. There we go. So just a quick background. You know, how did we even come into being, right? So we look at the world, we saw that really the punchline is that the legacy design software was becoming the bottleneck, right? You had new manufacturing technology, you had new computational technology, new ways of representing geometry, but the legacy systems weren't keeping up with that, and they were kind of starting to become the friction point in the design process. And so that's really where we saw the opportunity to really implement some of these new technologies and really unlock more of the value that's offered from additive manufacturing. So really our mission, when we think about what we do every day and why we do it, it's really just enabling engineers to design the most transformative products, right? Or if you want to use the word innovative, that was mentioned in this event, that's really a lot of what we focus on. So, you know, each day it's not just designing better products, but really pushing the boundaries of everything that we do to make sure that at the end of the day, the engineers who are using our product are capable to do things that, you know, maybe they didn't think were possible with previous tools. So that's really what we show up every day to do, and we love doing it. So some of the things that go into our product and kind of how we do what we do, there's kind of these three core technology pillars. There's what we call this unbreakable geometry, which is the implicit modeling technologies, which is what we'll primarily focus on today. And then there's other aspects, reusable workflows, being able to automate things, to make design changes very quickly, enable design space exploration, and then field-driven design, which is a really interesting way to kind of leverage spatially varying data, like a stress simulation result, and use that to directly drive the geometry. So each one of these technology pillars could probably be a 30-minute presentation in itself. I think I have about 5 minutes to go through the first one, so we're only going to skim the surface, but we'll get through it. So on the modeling technology front, really, when we looked at it, we really start from first principles. And what I mean by that is, when you look at how things are done traditionally, on the left-hand side of the slide, there's the boundary representation, right? So usually what's used in your traditional CAD systems. And in those systems, you have edges and faces and all this topology. When you do like a Boolean operation, it has to do the actual numerical intersections between all this geometry and then come out with the result. And the implicit representation, which is what nTop uses, it's all a sign distance function, more or less. So a sphere, to do like a union, it's just the min of the sign distance field of these two spheres and you're done. So it's very, very simple. It's very lightweight. You can parallelize it very easily, which is in the product, things are multi-threaded as much as possible. So that's the basic, I think the most fundamental aspect of what we do is this implicit modeling technology. The sign distance field representation is really what makes the whole thing go. And when you look at, this is just a snapshot of some organic structure from a bone, very complex, a lot of spatially varying features. This is something that you're not going to sit down and model up in your traditional CAD tool. So we looked at something like this, is like, how could that be done with our technology? And when you apply the implicit approach, that's really where it starts to shine, right? So this is a similar part, very porous structure, smooth blends around the joins of the shell structure, spatially varying features. And this is the type of stuff that the implicit representation really shines on. And on top of that, when you look at how it's implemented, it scales really well. So whether you're in this simple slide where, something that's one single unit cell, maybe hundreds or thousands, it's all essentially one equation. And so that it scales really well. The extra complexity that you may want to model doesn't cost you in terms of file size, which can cause downstream issues as you go to other tools. So that was another benefit of this approach. So that's a little bit on the modeling tech. We could go a lot deeper with more time for sure, but just kind of a snapshot of like where we're used in the world, right? So a lot of what we do, aerospace and defense, they're in a lot of cases looking for any and all ways to get weight out of their designs. There's a lot of unique things that you can do with these types of advanced representations of geometry to get lighter weight parts. Automotive, similar kind of objective, but also looking for things like crashworthiness and be able to tune structures so that they behave a certain way in maybe crash scenarios. And then the medical industry with kind of the osteo integration applications, and then consumer products. And this example is just showing a surface texturing application on something that looks like an iPhone case, just be able to generate that type of geometry. A few more examples and a little bit more detail. So heat exchanger design, this is one that we recently did with a few partners, and it actually uses nTopology to do the design work, and it was coupled with, I believe, ANSYS Fluent to do some of the CFD calculations, and in the process, was iterated until they eventually got to a weight reduction, but also higher performance in terms of being a heat exchanger. So that was something that we did recently, just kind of an example of the types of geometry that you can generate with this approach. Another, like I said, medical is a big one. So, implants, being able to generate these types of porous structures very easily, being able to process them. A lot of our use cases in this space, they're not just generating one part, they're generating a family of parts with new inputs. And so the modeling technology not only allows you to generate the geometry, but also when you do make design changes or want to do a variation of your part, it's very, very robust. So it will actually run and generate new results, which is a plus. And then last, just an example, consumer product design. This is a piece of a shoe sole. So in this case, there was 3 zones they were looking at, and they had different a pressure field for each, and they wanted to spatially vary the lattice structure according to that field. So this was using a combination of the modeling technology, but also the field-driven design approach that I mentioned early on. So that was kind of a quick overview of where some of these representations come into play and the types of value that they deliver. A few quick notes on what we've been up to recently. We recently released version 3.0. With that, there was our first step, kind of implementing more GPU technology in the product. So this example here in this video, you're seeing as you now kind of slide one of the variables in the tree there on the left-hand side, the geometry is updating in real time. And part of the motivation was that as a design tool and a designer, working with this type of software, the faster the software responds to your thought process, essentially, the more intuitive that things are going to become, the more creative the person can be. There's not that lag in, changing a variable and then waiting even just a couple seconds for the geometry to update. But the faster we can make it, the more creative the user can be, and really get a feel for that design space and kind of explore it in new ways. One quick note on something that we've been working on recently, that's just an idea we have. When we look at what we do with the implicit modeling technology, it's a new representation, and we're just one tool in a very large ecosystem of tools that all have to come together to get the job done and get a part built. And as a part of a side effect of the GPU work, we realized that we can take what we push up to the GPU and essentially write it out into more or less a text file that can then be consumed by other tools. And so this idea of implicit interoperability has been something we've been experimenting with. So in this case, nTop can generate this, what we call a code rep for short. That code rep, we've prototyped a few implementations where we're bringing it into NX, brought it into NetFab. And we think this has the ability to be another kind of interchange format. So it's something that it's just an idea we're exploring, but we're pretty interested in seeing where it goes. A few more examples. We took the code rep representation of the implicit geometry and put it into this product, a web viewer by Zia. And so what you're seeing here is there's a section cut with the geometry around it, and then through that there's the TPMS structure there in the middle. So that's the code rep being loaded into the system and rendered without meshing or doing anything like that. And on top of that, the variables that you may have exposed in nTop, like your design variables, are coming through here. So on the left side of this image, you see these sliders. So now in another tool, you can do slides, or you can adjust things like you could in nTop, and the geometry is going to update there. So it's a way to communicate to another tool without losing any precision of the implicit representation. And one other example we did with a company called Intact Simulation, we took that code rep representation, sent it to some of their simulation technology, and they were able to do a thermal analysis without ever having to mesh the complex geometry in a traditional sense, right? So they have some unique technology that can work on signed distance fields. And so that's super interesting. A lot of customers who are using our product, we've made it easy to generate the geometry. They can now manufacture it, but in some cases, when they hit that simulation step, that's kind of where the bottleneck is now starting to emerge. So this type of technology is something we're really interested in. So this whole idea is, we're really trying to make sure that the technology that we build and is perfectly useful to design parts, it needs to work with a wide array of tools. And so we're continuing to discover new ways to communicate with a complete tool chain and go from there. So I think that was all I had. A quick overview. I know I only skimmed the surface. If anyone has any questions, please feel free to reach out to my email. I'd be happy to go into any more detail. Again, thank you for having me, and really looking forward to seeing the results.
Thank you so much, Trevor. Wonderful. We really couldn't have hoped for a better technical partner. So thanks a lot again. How's the weather like in New York City today?
So far, so good. Nice and sunny.
Wonderful. So enjoy the day, and of course, feel free to stay with us and seeing the results. Okay, so I'm sharing back my slides. This should be the right one. We will soon find out. Yes. Okay, so now it's time to know the results provided by the team. Okay, so each team will have 4 minutes of time to present their results. Okay. Right before each team, each company will be presenting very briefly, in only 2 minutes, the company and why they have decided to take part in the PROTO challenge. Okay. After the presentation of each team, the mentor of that team will have the chance to ask one question very briefly to the team, and the team member, I mean the speaker, will have 30 seconds time to reply to that question. Okay, so the time is really strict. Everybody makes sure you have a timer along with you, which measures the time, because you will have only 2 minutes time for the companies and 4 minutes time for the solvers. And of course, I remind you that after the presentation of all the 5 teams, we will also have a keynote speaker from Paolo Gennaro, turnkey and research projects at GF Machining Solutions, with a speech about additive manufacturing. When does it really make sense? Okay, so stay with us until the end, also because you want to know who is the winning team. Okay, so with that said, I will give the floor to Vesna to introduce the first speakers.
Okay, thank you, Nicola. Well, the first speaker is the team 1, Linkotech. So I will kindly ask to Elisa Alboni to share the screen, and I will pass the mic to Robotti Francesco. Please, the floor is yours.
Hello, everybody. Thank you for the invitation. So I introduce Linkotech, that is, next please. That is an industrial group. It's working on 4 different fields, from power energy production to medical device to aviations to manufacturing equipment. In all, we have based with 16 manufacturing plants globally, 8 in the United States, 7 in Europe, and 1 in China. It's a company that employs more than 1,100 people in the world. So as you see, we operate with technologies from thermal plasma spray to additive manufacturing to CNC casting and polishing, and we have R&D centers for the different application. Next, please. These are the operation. Next, please. Today is the day of Linkotech Medical. So this division takes care of manufacturing of implants to replace injured parts of the human body. For doing that, we use different technologies from machining, casting, and surface treatment, till the final cleaning and packaging before sterilizations. And additive manufacturing is one of those technologies. Next, please. So today, next, please, we see the help Linkotech Additive bring to the Linkotech Medical, putting in place the capability of metal additive manufacturing. Now we operate with 26 metal printers to manufacture basically titanium alloy and sometimes cobalt chrome or stainless steel. The output from additive manufacturing is now for more than 100,000 pieces annually. So we are a serial user of additive manufacturing. Next, please. And today's contest is try to change a little bit our minds. So move from the serial production that is in our DNA for more than 10 years to what was called before mass customization or personalizations of prostheses that actually exploit even better the full capability of additive manufacturing. So we will challenge ourselves in the production of custom-made parts in a very fast and short delivery time. And I leave the floor to Elisa.
Okay, thank you. I'll just share our presentation. Okay, so good afternoon, everybody. I'm Elisa, and I represent Team 1, who collaborated with Linkotech to the design of an innovative hemipelvis prosthetic device. Here in the slide, you can see the initial component. I mean, a custom hemipelvis prosthesis, additive manufacture made of titanium alloy. The aim of our challenge is to optimize this initial component in order to develop a new type of medical device. So first, the total weight of the device must be decreased so that it resembles the one of the real bone. Then porous structures are to be added to enhance integration, and so the process known as secondary fixation. It is important that the transition between the different parts is smooth so that no crack starting points are created. The last aim of our challenge is to achieve a versatile workflow for a fast design and production of similar components. So first, we perform a static analysis of the initial product in order to evaluate its performances. The load is assumed to be evenly distributed on the upper half of the acetabular cup, as shown by the yellow arrows, and is set equal to 5 times the body weight. On the right, you can see the green dot representing the nodes which are subject to a displacement restraint. Employing this load case, we got this result, which are a maximum stress of 170 megapascal and a maximum displacement of about 50 microns. As one of the main problems associated with this kind of component is that their weight is way higher than the one of the real bone, a topology optimization is set up to minimize the weight of the design. Employing the same load case presented previously and adding some passive regions and geometrical constraints so that the functionality of the component is preserved, we obtain these components shown in the slide. It is important that the initial shape of the component is preserved as it sustains surrounding tissue. Therefore, the removed part is partially filled with structural lattice. In particular, we chose a derived structure with 1 millimeter of thickness, as it is a self-supporting structure with good structural resistance, compatible with soft tissue, and suitable for contaminative purposes. Then, porous layers are added to boost the adhesion and proliferation of bone cells and to promote the growth of new tissues. All the parts are joined together so that a smooth transition is achieved. As you can see from these close-ups, the porous size changes gradually from 0 near the bulk substrate to the maximum value of 800 microns near the surface. These components must guarantee integrity and functionality over a long period of time. Therefore, the blended radius is optimized based on the result of the static analysis of the component shown in the previous slide in order to increase the fatigue resistance. Thanks to this improvement, we got a 25% reduction in the maximum stress of the component. And as you can see from the static analysis of the final component, the process is more evenly stressed. And in particular, the maximum stress is about 440 megapascal, while the maximum displacement is about 200 microns. So what did we obtain? Starting from the initial component on the left, we got a cutting-edge new component, which is 62% lighter than the initial body, with excellent predisposition to osseointegration, and which promotes nutrient exchange and vascularization, both thanks to the structural lattice and the porous layers. Moreover, thanks to the mechanical properties that we achieved, which are similar to the one of the real bone, the stress shielding effect is potentially reduced. Last but not least, the workflow employed is created so that any parameter can be easily changed, and so the workflow can be easily adapted to the development of a large variety of medical components, such as spinal cages, as reported in the report. Here you can see the picture of the printed optimized component provided by Linkotech. So, yep. And I would like to thank you for the attention.
Thank you so much, Elisa, and the whole team number one. Now it's time for the mentor, Simone Murchio from University of Trento, Industrial Engineering Department, to come up with a short question for you. Go ahead, Simone.
Hi, Elisa, and hi, everybody. My question regards if you can give more details about the last FEM analysis you showed, and particularly if you have considered other intermediate models and simulations.
Yeah, thank you for the question. So let's consider first that the porous part is made of elements which are 0.3 millimeters thick. Therefore, a huge amount of computational resources would have been required to simulate the whole component with just solid elements, because the tolerance for the mesh would require to be quite low. Therefore, we developed two alternative approaches. The first one, we just meshed and simulated the gyroid part and the bulk substrate with solid element. In this way, we obtain the behavior of the structural part of the prosthesis with low computational cost, as the tolerance could be increased. In the second approach, we also meshed the porous part employing beam elements. In this way, we obtain basically the behavior of the wall structure with slightly higher computational cost. As the results obtained are comparable, the two approaches can be stated to be equivalent and so feasible for our case. Moreover, recently, thanks to Linkotech and the PROM facility, we got the opportunity to further validate our results, employing more powerful machines to simulate the wall component with solid element and appropriate tolerance. So, yeah, these are the three models that we consider.
Thank you so much, Elisa. Thank you also, Simone, of course, for supporting team number one, and congratulations to the whole team number one. First of all, for making it until the end of the challenge. That was not, you know, taken for granted. So congratulations so far. Thanks again. Keep it up. And in the meantime, you can all see that Professor Bosetti and Professor Benedetti are scrutinizing the results because the evaluation is still open. So good luck again to all the teams. Okay, so now Vesna, who's next?
Next, we have team 2 with Francesco Martini, who is going to share the screen for Fabrizio Defant, who is going to present PAMA. Please continue. Sorry.
Good afternoon, everyone. I'm Fabrizio Defant, and I'm involved in the R&D department of PAMA, where we design and manufacture milling and boring machines from medium to large dimensions. We have a history of over 19 years, and our headquarters is located in Rovereto, while we have other 2 plants in Castelmella and Lingang in China. Over the 75% of our production is exported overseas, and we have customers among some of the major players in the sector of energy, aerospace and defense, earth moving, naval, railway, and general machining sector. Our strengths are the high level of customization of our systems and the quality of our services. In the R&D department, we aim the innovation of our systems, services, and also the manufacturing process. Next. Okay. We have decided to participate to PROTO Challenge, proposing the redesign of the intermediate body of a universal head attachment, which gives 2 additional rotational position axes to the tool in order to perform particular machining operation. The intermediate body is characterized by a complex net of drills, which brings pressurized fluids from the fixed part of the machine down to the spindle body of the head attachment. Aside from other more specific aims, the first goal of PAMA is to understand how far is additive manufacturing from being applied successfully to large and heavy components. We'll see the answer in a while, thanks to our team. Thank you all, and Francesco, the stage is yours.
Francesco, you're muted.
Okay. So this is our team, Matteo Perini, our mentor, and then all the solvers. And starting from PAMA's goal, we settled down those 3 main purposes. So simplifying mechanical processes, but ensuring interchangeability. Then lightening, keeping a similar mechanical response regarding the displacement of the tooltip. And here you can see the path that we have followed for the last month. So initial component analysis, then channels redesign, so material selection and topological optimization, then choice of volume threshold and optimized component analysis. Here in this slide, forces that the intermediate body has to withstand are reported. Some of them, those 3, are due to the locking mechanism of the rotation system. And down on the left, there's the machine side fixed phase, then the upward thrust on the tooltip, and the forces on bearings. So defining boundary condition and loads is the starting point for the FEM analysis of the original body. And at this point, it was necessary to introduce this auxiliary cone in order to measure the displacement of the tooltip, so to set the topology optimization constraint regard stiffness. Instead, result on stress field are then used to understand where new channels have to be placed. Therefore, we chose to avoid those high-stressed regions, so to ladder as much material as possible in order to increase stiffness. And here on right, you can see channels evolution. And you can notice that additive manufacturing lets much more freedom during design. At this point, almost everything was fixed for topology optimization. So recalling PAMA's goal, or rather evaluate the possibility to produce the object in question through additive manufacturing, the final printed product has to be as cheap as possible. And that means that the optimization goal is a weight minimization. Then some constraints have been fixed. So limiting the displacement of the tooltip, then defining some passive regions and limiting the stress field, hence to satisfy a certain safety factors. And other input for optimization process are material properties. However, during material selection, it has been taken into account not only characteristics like stiffness, strength, or density, but also process-related factors such as printability and availability on the market, powder's cost, and problems related with support removal. Therefore, we selected these two materials, precipitation hardness stainless steel and an high-performance aluminum alloy. And after testing both of them, we determined that the 1740H behaves better for this purpose. So after the first iteration, thanks to additive manufacturing advantages, appeared the possibility to modify one channel to increase bearing cooling rather. And then repeating the whole process, some optimized body with different volume fraction threshold have been tested with an FEM analysis in order to get the best one and to check if the company's requirements were fulfilled. So final results. Thanks to additive manufacturing, our optimized component shows a mass reduction of 45%. Then thanks to the new pipe, the bearing cooling is enhanced and the stiffness requirement fulfilled. Moreover, a new space where electronics can be located appears there. And last but not least, the machining time is reduced by 60–70%. So now we can answer to PAMA's first question. Additive manufacturing, it is not that far from a real application thanks to an optimized design. And in the future, if the whole boring machine will be topologically optimized, it will be possible to change the interfaces of this component and accordingly the input and output position of the redesigned channels. While in this project, those points are assumed to be as constraints. Moreover, the electronics and pneumatics position could be changed from above to the side zone there and placed in a polymerics printed box. And in this manner, it will be easily accessible for maintenance. So thanks for your attention.
Thank you so much, Francesco Martini, and also the whole team. You have actually used almost 5 minutes and a half. So now it's time for you to reply to the question to the mentor, Matteo Perini, but you will have to be very quick in doing that. Okay, so Matteo, the floor is yours.
Good evening, everyone. I'd like to ask you if you used some special constraint to improve the printability of this object.
Yeah, we try to minimize support with nTop, but the result that we got was not that useful. But then we were wondering that in the future with binder jetting, we will not need support. So well, it's all.
Okay. Thank you very much, Francesco. Thank you, the whole team, number 2. And thank you especially to Matteo. And as you have seen, the challenges were really challenging. And sometimes we had some phone calls with the mentors who were a bit worried themselves about the feasibility of the challenge, but you have made it. So congratulations. So the team number 3, who's next?
We have Marcello Tenca, who is going to share the screen for Emiliano Leoni for the 3rd challenge, which is the one of Leoni and Leoni and Giulio Vianello with Evopad.
Buonasera a tutti. Giulio Vianello è un insegnante di scienze motorie. Ha un passato da atleta e di buon livello e da circa 25 anni si occupa di preparazione fisica, attività motorie orientate al benessere della persona. Lo studio e soprattutto la sua esperienza sviluppata in questi anni di lavoro sul campo con atleti e non, lo ha portato ad avere la voglia di sintetizzare in un unico attrezzo molte delle applicazioni che utilizza tutti i giorni nella sua professione. Io sono Emiliano Leoni, attraverso il mio studio Leoni e Leoni mi occupo di architettura, ingegneria e paesaggio. Lavoro cercando sempre la miglior sintesi possibile tra la forma, la struttura e la materia. E dall'idea di Giulio ho sviluppato il design di Evopad. Evopad è una tavoletta, un attrezzo utile all'allungamento delle catene miofasciali per il ripristino di una corretta postura. Evopad potrà avere un'evoluzione per un utilizzo più ampio e polivalente, legate alle attività di potenziamento muscolare e riabilitazione funzionale post-traumatica e post-operatoria. Al team 3 della PROTO Challenge abbiamo chiesto di semplificare il design generale della tavoletta, ottimizzandone il peso, lo spessore, la resistenza, ma sempre nella ricerca del miglior connubio tra design, ottimizzazione e funzionalità. Il tutto doveva rispondere sia alla tecnologia della stampa additiva per le preserie o le future customizzazioni, sia per lo stampaggio per la produzione definitiva. La partecipazione alla Proto Challenge, attraverso il sapiente lavoro del team e delle opportunità tecnologiche, ci permette di ipotizzare la creazione di una startup per la produzione di Evopad, visto l'interesse già dimostratoci di aziende del settore. Il team 3 è stato il nostro dipartimento di ricerca e sviluppo e per questo vi ringraziamo.
All right. Thank you, Emiliano. Okay, so, all right. Good afternoon, everyone, and thank you to be here. My name is Marcello Tenca, representative from Group 3 of the Proto Challenge with Giulio Vianello and Leoni. And with this presentation, I will quickly show the main steps that led to the proper design of the product that was assigned to the team, which name is Evopad. Before starting, please allow me to present the participants from Team 3. Matteo Bonato, Matteo Bonetto, and Federico Borin from the 3rd year of Industrial Engineering, Luca Del Giudice, Lorenza Dotta, and Cinzia Maestranzi from the 1st year of Mechatronics Engineering, our mentor, Raffaele De Biasi, PhD student from the University of Trento, and again, myself, Marcello Tenca, from the 1st year of Materials and Production Engineering. So there are many causes that can lead to backache. Let's think, for example, when we hold our phone in a wrong postural position. It is from this common experience that Evopad was conceived. In particular, it allows the proper execution of the so-called proprioceptive exercises, which aim to the restoration of the backbone muscular chain. Evopad has been designed since the beginning with a circular economy approach, meaning that every step of its life cycle was thought and meant in order to minimize its impact on the environment. And on this purpose, a materials guide has been given to the company as a sort of booklet for a sustainable production of Evopad. So this is the original CAD that was presented to the team with the forces acting on it. However, the withstanding of the load was not the only requirement, but there were 3 more. 1, Evopad had to be compatible with pre-existing gym accessories, such as the elastic bands that you can see in the picture. Second, it had to be eye-catching and to make perceive to the final customer a high perception of high premium quality. And third, it had to be printable and manufacturable with both production technique, 3D printing for the initial prototypes and injection molding for a more large scale production. It took soon to realize that the original CAD proposed did not match all of the requirements. So the team opted for a functional decomposition process, meaning that different concepts were skimmed starting from scratch until the last best working CAD was found in order to be optimized. Then FEM analysis were run. And in order to do so in a more accurate way, research analyzing 1.2 million foot scans was used in order to better understand the exact scalar field that a human feet was exerting as a pressure on Evopad. Once the most stressed area were found out, the topological optimization could take place. In this stage, the homogenization technique was used. Basically, the team created a fictitious material made that had the same mechanical properties of an optimized cell, but gave this material to the unoptimized, assigned this material to the unoptimized full body CAD, so that the results were still accurate, but the meshes were way more simple and the calculation took less time, so that the team could perform more simulations. And this is the final render of Evopad. As you can see, it is lighter, it is thinner, it is eye-catching, compatible with all the accessories, it is producible with both 3D printing and injection molding, and it is sustainable. I would like to end with the team's most astonishing result, which is a reduction in weight of 29.7% from 1.5 kilograms to just 950 grams. And the team is proud to announce that this is Evopad, versatility and innovation with a careful look to the world's future. Thank you very much for your attention and enjoy your fitness with Evopad.
Thank you so much, Marcello, and the whole team number 3. Now it's time for your mentor, Raffaele De Biasi, to pull up a question for you.
Thank you, Marcello. Let me ask if there were some particular complication during the optimization process.
Yes, well, thank you for the question. I think that probably the most challenging part during the optimization process was the fact that Evopad was thought to be so versatile. So it was meant to be used in different ways. The final customer will probably apply loads and forces in different positions. So it was hard to find parts of the material that were not stressed. And therefore it was hard to find useless material that could be removed. And that is why we are so proud of the 29.7% weight reduction.
Thank you, Marcello, again, and thank you especially to Raffaele De Biasi for mentoring team number 3. So now it's time for team number 4 to present the results and the company briefly presenting itself.
Yeah, I will give the floor to Luca Ravacchio, who is going to share the screen for Matteo Iellici for La Sportiva.
Sorry, do you hear me?
Yes.
Yes.
Okay, hi to everybody. So La Sportiva, it's a company leader in the outdoor industry, is based in a small valley in Val di Fiemme in Trentino, is still owned by the family that is strongly connected with the territory and the mountains. Mountains is our environmental, where we are at the shadow of the Dolomites, where we design all our products. We have different production locations all over the world, Asia, East Europe, and But one of the most important is here in the valley, where we are around 400 people, where we produce mainly climbing and mountain footwear. The challenge that we proposed to the group, to the team for, was linked to one of these products, is one components that we use on the production of specific and technical mountain boots. We call it lasting board. That is the main structure, the body, where we build the boots. The challenge behind this project was improving performance. Actually, improving performance is always a goal that we have. In this case, improving performance means for us reducing weight and working on the forces and on the torsion properties and on the strength that the components itself has to have. We are used to work also on the carbon fiber, where we ask for also working and finding solutions that are behind the carbon fiber. So I leave the speech to the teams that explain the work that they are behind the products. Let me say thanks to all the teams and the guys that work on that, because we saw a lot of enthusiasm, and they are really involved on the project to understand what there are also behind, not just all the single components, but behind the project that we are in mind. Please.
Okay, so thank you. Good evening, everyone. My name is Luca Ravacchia, and I'm here representing Team 4, La Sportiva. Here you can see our smiling faces and the roles that we chose as solvers, and also our mentor, Ciro Malacarne from ROM facility. The proposed challenge was to redesign the insole of an ice climbing boot with the goals of reduce the thickness, reduce the weight, increase the stiffness. The initial conditions that had to be respected during the redesigning process were to maintain a region at the lower surface edge with a width of about 20 millimeters to assure the gluing of the insole to the climbing boot, and also to maintain a minimum thickness of about 1.2 millimeters, since it had to be produced by injection molding. For starters, the team decided to model in nTop both flexural and torsional analysis, keeping in mind the real testing conditions. Here, the flexural analysis is represented in a 3-point bending test. The test was modeled after La Sportiva's own testing setups and results. The torsional analysis was also modeled after the most used torsional test setups, by allowing only rotations and applying a torque on the tiptoe. With both flexural and torsional analysis performed, we moved to meshing. As the nTop results were checked in ANSYS with parameters such as skewness to evaluate the element quality. Here we can see the results of the FEM. I wanted you to focus the attention on the location and shape of the loaded area. It will come in handy later on. Also, the FEM results on the torsional analysis are shown. After finishing with the FEM part, the team moved to the topology optimization of the combined flexural and torsional models. The main results are here shown in progress. As problems with constraint conflicts were solved, the final optimization is here shown. After consulting with a professional mold operator, the team decided to opt for a peculiar sunburst design to ensure both structural support and good melt flow, starting from the injection point in the ray's origin. The rays have a trapezoidal cross-section to ensure an easy mold detachment. Here also the results in weight reduction are represented. Okay, and the optimized component analysis is here shown. As we can see, the maximum displacement zone is increased, allowing for a better mobility to have control during climbing situations. Also, the torsional analysis is shown. In this slide, the process of the team is represented as we move from the starting situation to the topology optimization and then the final design. As you can see, the weight is reduced by 69.45 to 68.63, and the other characteristics are maintained. Also, the workflow is here shown for both flexural and torsional analysis. For future improvements, the team suggests to look for different materials, such as single polymer composites, which are easily melted at the end of life and reused. To look for different designs, as with more time on our hands, we would for sure investigate new shapes. And also a solution for the sponsorized La Sportiva athletes is presented, and it's 3D printing, since a personalized insole can be produced using the pressure map from the athlete's feet. In the end, we wanted to thank the HIT staff, our mentor, Ciro Malacarne, for his availability and his counsel in the moment of need, which were many, and La Sportiva, in particular Enzo Jellici, who accompanied us during all the process, for his interest and willingness. And at last, thanks to the public for the attention.
Thank you so much, Luca and team number 4. Now it's time for you to have a question very quickly from your mentor, Ciro Malacarne. Ciro, go ahead with the question.
Hello, everyone. And thanks. I want to thank the team because it has been a pleasure to work with them. So my question is, how did you obtain the optimization after merging the two models?
Well, we noticed that there were, say, inconsistencies between the constraints. So we used the same constraints to mix both torsional and fractional analysis. And in the end, we had to move the load from the metatarsal zone to the end of the foot, or to the tip toe, and to, let's say, model it as a cantilever.
Very good. Thank you very much again, Luca, Ciro, and the whole team number 4. And now we get to the final team. Last but not least, of course, team number 5. Vesna?
Yes, we have Davide Doriboni, who is going to share the screen and after to present for solid power, and Daniele Lane, who is going to present the company. Please.
Good afternoon to everybody. I'm going to present solid power, this activity. Can you go to the next? Okay. Solid Power is a company that have various plants around the world. The center is in Italy, but we have also a plant in Germany, Switzerland, and Australia. And the company develops, manufactures, and commercializes fuel cell micro-cogenerators for the production of electricity and heat. The base technology, so the micro CSP, is based on solid oxide fuel cell that are stacked and assembled in a stack. And we are present at the moment on the market with one product, the BlueGen BG15 micro CHP, that have a nominal power 1.5 kilowatt and the electrical efficiency net DC of 60%, so very high, and the cogeneration efficiency 85%. Next, please. We have under development new micro CHP, bigger one, with 6 kilowatt of nominal power. And inside this project, we ask to the Proto Challenge team to optimize manifold, structural manifold that have to provide fuel and air to the stack, and as well to support the stack of the fuel cell. This component usually work on temperature around 650 degrees, and is characterized by a thermal gradient that is the main provide the main stresses on the components. So in principle, the analysis have to be performed on the thermal side, let me see. And the goal is to reduce the deformation, so or to keep as the flatness as much as possible on the interface between the stack and the manifold. This because this interface have to be gas sealed, so it's also a safety related problem, as well of the performance of the system. So I can let the floor to the team to explain the activity.
Okay. Good afternoon, everybody. I'm Davide Dorigoni, and with Team 5 in collaboration with Solid Power, we worked on the Proto Challenge 2021. I'm sorry. Okay. So the stack manifold presented is in the center of this slide. As we can see, its role is to connect the main piping to the stack of the solid fuel cell. The important thing is that the upper plate has to remain as flat as possible in order to do not allow any leakage of fuel outside in the environment. So we took this into account, so the planarity plus a good material characterization into the optimization process. So as an initial condition, we set a thermal load and a battery weight on the piece. And moreover, we cannot change everything of the stack manifold. We cannot change the upper plate, and we cannot change the pipes. And we do not want to allow any rigid motion. So we started with a thermal analysis of our stack manifold with properties of the material at ambient temperature. And then we use those results in order to characterize the properties at the working temperature and achieve a more detailed thermal analysis and temperatures in general. So here we can see the difference with the deformation of our stack manifold. And we started with our topology optimization, but we had a problem. So the nTopology software that we were currently using do not allow for thermal load in the topology optimization. So we had to change our route to find another way around this problem. And we did that by modeling the thermal load as a distributed pressure, or as two lines of pressure on the top of the stack manifold. In this way, we are able to mimic the effect of the deformation of the thermal load. So we started with different starting boxes where we can try to set a path for the optimization in order to change some parts more than others. And here we combine, we allow to see the effects of the thermal load and the forces that model the thermal load. They're quite similar. So we set up our topology optimization with constraints and the objective to minimize the displacement along the y-axis. And at the end, we used MATLAB in order to translate from user requirements into engineering requirements, because planarity is a quite difficult to translate property. So we had to use the standard deviation on the surface of the points on the surface and the maximum height difference. We realized a map of every and each solution where we combine these two aspects. And the best solution that we found was the CK battlefold that is on the bottom left of the map. So it has the most outstanding standard deviation and the best maximum height of every solution. And here is a more clear picture of it. And so we improved a lot the planarity overall. And as I look in the future, we would like to see how the piece could be changed in order to make it realizable for casting manufacturing. Thank you for your attention.
Thank you so much, Davide. A very quick question from your mentor, Gianluca Berti.
Hi to everyone. The question is, how was the thermal analysis carried out?
Okay, so we started by setting the inner pipes temperatures at the temperatures of the fluid that flows inside that we had from our company. And then we set the temperature of the outside environment, and we carried out the thermal analysis using the nTopology block, and that's it.
Wonderful. Thank you so much, Davide, again, and Gianluca, and the whole team number 5. So all the presentations were provided, and now the jury members can wrap up their evaluation, so they can now sort of retreat and discuss if there is a need for discussion. And in basically 15 minutes, we will be communicating the winning team. Anyway, you have seen already that all teams made outstanding results, but we will know soon who will be the winning team. In the meantime, I see that Paolo Gennaro already switched on his own video. So, hi, Paolo, how are you there?
Ciao, buongiorno. Hello, good evening to everybody.
Good evening,
I'm trying
ciao.
to share now my screen.
Yes.
So we can jump the presentation.
Yes, now it's time for Paolo to provide his own keynote speech entitled Additive Manufacturing, When Does It Really Make Sense? Paolo, the floor is yours.
Hello, I tried to put together all my experience for the last 15 years to give an idea of what does it mean for me additive manufacturing. So at the beginning, a few words about my actual company is GF. GF is a Swiss corporation, 3-area business. The first is piping system, producing system to distribute water and gases, not allowed with additive. Casting solutions, several facilities around the world making iron casting, investment casting, and also additive manufacturing. And then machining solutions is a worldwide leader in milling machine, EDM machines, G-Sharp mill is very well known. And we are also producing together with 3D Systems additive manufacturing machines. So first, the concept for additive manufacturing that for me is very different from rapid prototyping. Why? Additive manufacturing is an industrial process where quality is mandatory. The price is very important. Rapid prototyping is something where it's important to arrive with the product as soon as possible. Quality is what you get. And the price, you may accept what is coming because of the delivery time. So for additive manufacturing, for me, is the best compromise between design, machines, and material. As everybody knows, and is already highlighted during this presentation, most of the time is based on topological optimization to reduce the part count, avoiding joining and welding, and to minimize build time and post-processing operations. But this is only for the geometrical optimization. In most of the cases, to be competitive in additive, we have also to optimize the material. So go through powder to material that is not possible or very difficult to cast, very difficult to forge, or quite impossible to mill from a block. For this reason, also the powders are becoming very important because we need dedicated powders, but also because going in production with high volume, We need to take care of the risk of the cross-contamination. Imagine we have a machine with 1 ton of powders inside. We make a mistake and we mix 2 kinds of powders. Result, we trash the part, we have to clean the machines, and we trash all the powders inside because are different, strange mixed powders, and probably we are not lucky, we are not producing a very competitive new alloy. But also going to the mass production, we have also to take care of the health and safety of the powder. So we can probably not anymore work with the plastic drums, 10 kilos each, to load, for instance, 1 ton of powders because of the emissions that these small powders are going to make into the ambient, and because of the cost of the disposal of the plastic drums. So powders are also very important. And then machines. When we talk about machines, everybody's thinking, okay, the printer, but there is not only the printer, because hopefully the company, the customers want to produce a finished part. It's quite impossible to produce a finished part starting only from the printer. We need to add all the post-processing, milling operations, EDM operation, turning operation, also other operations like laser texture or laser drilling for the holes. So when we talk about machines, we have to think about the full portfolio of machines needed to produce one part according to a drawings. And now we arrive to the value proposition in additive, that at the end of the day is from the CAD, making a good design in terms of topological optimization, but by the point of view of the manufacturer, we have to put together the subtractive with the additive in order to maximize optimize as much as possible the cost in production. We don't want to spend too much time in milling, or we don't want to spend too much time in printing, but we have to arrive to the best compromise, starting from the data preparation, the printing, to the post-processing. Why? Because at the end of the day, in my experience, nobody will invest to increase the cost of the product. To be competitive in additive, we always have to address a cost reduction and an improvement of the performance. This is my experience. How typically we do that starting from additive? Because we do not have a vendor tooling. In case of casting, it's very important cost, and you have to pay in advance. Then you put material only where needed, so means the part will be lighter. We have typically better material properties because the microstructure is typically equal everywhere, typically very fine. We have less material because the stock material needed then to go to the post-processing operation of milling and turning is typically 1 millimeter or even less. So the cost of the post-processing is less. The scrap rate is always typically low. From my experience, we go from 5 to 15%, in casting maybe also 50%. And the supply chain is short. And in most of the cases, the machine that is making the prototype can be multiplied, make the production. So it's easy to scale up. So I would like to go to example of industrial product to better highlight this concept. It's important to understand that the majority of the parts that you see here were designed or start the production 15 years ago. So it's not really a new science, as was allied by Linkotech. The tabular capsule, this biomedical devices, started their production roughly 10 years ago. Now I believe that the production is more than 100,000 pieces every year. And why it was competitive? Because at the end of the day, it was up to 100% of cost saving compared with the previous technology that was milling a bar, then making different coatings, and then making the other post-processing. Now the process is much cheaper, and the quality of the part is even better because the host integration is typically much better than the previous solution. And this was something that started roughly 15 years ago. And now, probably in Italy, we are leader in production of these applications, thanks to Linkotech and thanks to other company that started many years ago this business. Then we go to another product. We start from biomedical, where probably we have the biggest numbers, to turbine blades. Turbine blades is a particular product. We're talking about LPT, low pressure turbine blades making titanium aluminite. It is an intermetallic compound. It's a material that is very difficult to cast, very difficult to forge. And if you start from a forged part or from a casted part, you have to remove 3, 4, 5 millimeters of very strong material. So at the end of the day, going for additive, we have at least 50% of cost saving, more related to the saving in the post-purchasing operations. And the production was supposed to be in Italy up to 70,000 blades per year. Unfortunately, now the COVID complicated a little bit the situation, but these are the numbers on the plate. Then we typically go with the tools and die. In this case, the tools and die had advantage of the conformal cooling, as was the slide before. This means that the part will be much more expensive, but we save in production probably one press. For this reason, the part produced are typically 30% cheaper than the part produced with a mold that have no conformal cooling, and the volume are going up. And then the last are the fuel system. The fuel system are very well known. They start with the G, with the fuel system, the LEAP engine, but there are also a lot of fuel system used in industrial gas turbine, much bigger. The advantages and the reason to go additive was the fact that was possible to reduce the part count, but was also possible to improve the performance of the combustor. So were reduced a lot the emissions, and the TBO, the time between maintenance and overall, were increased a lot because there are less weldings in the area. The additive is fully welded, but there are less massive welding, and so the life of the component is supposed to be much longer. As you can see, as I was saying before, all these industrial applications, that are not prototypes, are industrial applications, starting in Italy 15 years ago, and achieved just now, or even in some years, a very huge maturity. But again, 15 years ago, I believe that now, if we want to go up with the numbers, we have to jump to a different model. In this case was industry to industry, or in case of the caps or biomedical industry to the hospital. If we want to go up with the numbers, going from 100,000 to millions, I believe we have to go to some consumer application, something that is produced by the industry, but is sold with the mass distribution, sold directly to the peoples. And I believe that is something that is still missing, because the growth of the additive is impacted a lot, but the fact that the industrial application of what is produced in high volume is not growing. It's roughly 5 years that I don't see very really big application that are making numbers. We always go around the same story, always see the turbine blade, molds and die, orthopedics, but at the moment I don't see a lot of new application. And probably is the fact that we need more creative people with high degree of engineering. This is probably what we need now to step ahead to go to millions of parts in production, not rapid in prototyping, but production. And again, we have to target at least 30% of cost saving. Otherwise, nobody will invest to lose money. And finally, this is the factory of the future. A lot of people think it's the factory of the future. In Italy, I believe I've seen 3 or 4 this facility. This means that we are not in a bad shape, also with the COVID. I hope I enjoyed the presentation. You are happy what I presented.
Thank you very much, Paolo. Yes, we are happy. Thanks a lot for sharing all your experience and helping all the participants to put into perspective what we're doing here at the Proto Challenge. So now it's almost the time for all the participants to know who is the winning team. In case you have connected only now, you are participating to the final event of the Proto Challenge 2021 edition. So all the presentations from both the companies and the teams were done so far, and also we have we had 2 keynote speakers. But before communicating the final results of the awarding, I would like to give the floor to my colleague Silvio Antonioni, Technology Transfer Manager from HIT, to tell you about an opportunity that you might want to consider.
Thank you, Nicola, for the floor. I will be very brief. I know the hype is very high to know who the winner is, but this I think is a good opportunity to the teams, to the company, no, they can have participating at this initiative. As you know, we are participating in a research project where we want to develop a social manufacturing framework to support open innovation and co-creation activity. We are searching in this project now, in this period, some new ideas to be explored, implemented within this factor with the strategies of co-design and co-development. So what does it mean? It means that we are giving 1,500 prize for 3 ideas. We will evaluate the 3 ideas. We will give hands-on support, mentoring, and commercialization support. This is an open call. You can see the deadline on the upper part. No, that is the next 30 June. The call is open. You can call us to have, let's say, some support on participating to this initiative. And I think it's a good opportunity to start from the end of the Proto Challenge and go ahead with iProduce. In the next slide, you have all the links to have a better look to the material and how to participate. Thank you, Nicola, for giving the opportunity to present this project.
Thank you, Silvio. So everybody feels free to take a snapshot of this slide because the iProduce project has something for you. Please do that and keep it up. Okay, so here we are. This is we are entering the final part of the 2021 edition of the Proto Challenge. As you know, all the participants have been evaluated upon 5 evaluation criteria that you can see here in this slide: the ability to perform the activities correctly, the completeness and the maturity of the results, the innovativeness of the results, the potential business impacts of the results, and also the effectiveness of the presentation. So now it's time for, I think, Professor Paolo Bosetti to open up his microphone and let us know about the review process and its outcome.
Thank you, Nicola. So it comes to me the hardest part of this day to nominate the winner of this contest, as it results from the joint evaluation of Professor Benedetti, Dr. Antonioni, and myself. It has been very hard to decide. Bear in mind that even if your works were all exceptional, we still had to rank them from the best to the worst. But this doesn't mean that the worst one is a bad one, absolutely. And this is exactly our case. All 5 teams have produced an excellent work. So now I'm going to declare the 3 best teams, of course, starting from the bottom of the rankings. But before that, though, remember that that Nelson Mandela's quote, which specifically applies to this type of competitions: you either win or you learn. So there is not a loser in this type of contests. This is personally something that I really believe in, and I'm really happy that our university, especially our department, offers plenty of opportunities to our students for learning by doing, challenging your skills against each other. That is the best way for the best way to learning, and the more fun too also. So coming to the final ranking, the 3rd place for the this year's edition of the Proto Challenge goes to team number 5, Solid Power. The 2nd place goes to team number 1, Linkotech. And finally, the winner for this year competition is team number 3, Leoni and Leoni. And I'm giving you my applause.
It never really works when you do these kind of things online, but we really try to make our best here. So congratulations to especially team number 3 that worked on the challenge provided by the project Evopad from Leoni and physiotherapist Giulio Vianello. I would like to invite now all the participants and the members from team number 3, along with, of course, Emiliano Leoni and Giulio Vianello, if he is connected as well. So guys and girls, feel free to switch on your camera now, because it's your moment. So everybody needs to know who you are. You're probably becoming famous, maybe not tomorrow, maybe in the future. So again, feel free to switch on your camera, because we now need to take a picture for the press. So you might end up in the press over the next few days. So let me see whether all the participants from team number 3 are there already.
Nicola, can you stop sharing the screen?
Yes, absolutely.
Thank you.
Okay. Yes. Hello, Giulio. I can see you. How are you, Giulio?
Beh, è una grande emozione, devo dire. È una soddisfazione incredibile. Sono rimasto quasi senza parole. Sono molto soddisfatto di questa cosa. È un sogno, diciamo, che da un certo punto di vista comincia a realizzarsi, perché è un po' di anni che io penso a questa cosa. L'incontro con Emiliano mi ha dato l'opportunità poi di approfondire alcune cose, e poi questa opportunità che ci avete dato è incredibile. Quindi io ringrazio tutti, ringrazio soprattutto i ragazzi che hanno lavorato in questi mesi, sono stati fantastici. Grazie.
Grazie a te, Giulio. I think that what Emiliano said before is great, that the team acted as the R&D department of this project. I mean, we're going to use that as a quote for promote the initiative in the future, for sure. So with that said, I think that I only need to mention again all the partners that made it possible for organizing and completing the Proto Challenge 2021. Of course, the University of Trento, especially the Department of Industrial Engineering, Trentino Sviluppo with Polo Meccatronica and the PROM facility, Confindustria Trento, Neutech Park, and nTopology. Thank you all very much. Again, it wouldn't be possible for HIT to, execute this initiative. But now I would like to invite all the companies, representative persons, and also all the solvers from the other teams, which made an outstanding job anyway, to switch on their cameras, because it's now time to take a huge snapshot. I think that what Vesna will soon do will be to scroll across the 3 or 4 screens of people that are into this Zoom meeting, and we have at least even more connected on the live streaming on our Facebook page. So now it's time to smile, say hello, and in the meantime, Vesna will hopefully take a few snapshots. So you can say cheers or something like that. This is, of course, for the press. It's not that I personally like to do that. So hello, cheers.
Yeah, it will take a little bit of time, but so stay freezed, okay? With a big smile.
Okay. Move on the right, on your right file. Okay, so that is it. For the people that have connected only now, do not think that we are crazy. We're just taking a picture here and waiting for it to happen.
Okay, done.
Fantastic. So again, thank you very much to all the companies and which presented very hard challenges. And I'm sure that the results that were presented by the solvers are going to be very useful to the companies. Again, as Silvio previously mentioned, the IPR, the intellectual property right of the results, are owned by the companies, because we want the companies to make the best of these solutions. And with that said, I would also like to thank very much my colleagues at HIT for making this possible. Silvio Antonioni, Vesna Misic, but also Andrea Sartori, Luca Mion, Camilla Martinelli, Cristina Boschetti, Serena Tonezer, and many other, including Arianna Conci, of course. Thank you very much, because this is really a teamwork that is behind the challenge. And with that said, if I am not forgetting anything, I would like again to thank all of you. We are a bit delayed on schedule, but I think we had fun. Sorry about that. The event was recorded and will be available in the future in the Facebook page of HIT. You don't need to have a Facebook account to see that, so feel free to go there, share the recording with whomever you want, your clients, your partners, your friends and colleagues. Thank you all so much, and hopefully see you next year. Okay. Bye-bye.
Bye all. Thank you.
Bye bye.
Thank you. Bye.
Bye.
Thank you.
Bye.
Bye.